Okay, good afternoon. First of all, let's check the audio. Can you hear from home? Okay. Okay, so today we finish our discussion on logistic regression. We started yesterday introducing the model. We said that the model for binary problems assumes linear separation that's of the kind W transpose X plus B greater or lower than 0, or in general, if we have non-uniform cost of errors, it will be the threshold that depends on the cost of errors. The prior is already embedded in the decision rule here. And we said that this score corresponds to the ratio between the posterior class probabilities, the logarithm of the ratio. And we have seen that this implies that we can compute the posterior probability of class C is a sigmoid function of, for class 1, for a sample xi, is the sigmoid function applied to the score. We'll see now to optimize, to find W and B that are optimal for our training set, in the sense optimal as W's and B that maximize the likelihood of our data. Then we've seen that likelihood maximization corresponds to minimization of the average cross entropy. The cross entropy is minimized when the prediction of the classifier corresponds to the label and when the prediction of the classifier are certain. So it's minimum when the classifier predicts with probability 1 that a point is from class 1 when the point is actually from class 1. And we've seen that the goal is minimizing the cross entropy. Well, that means that the classifier will try to have confident decisions that a point is from one class, and hopefully to minimize the cross entropy, it should be confident on the point belonging to the correct class. Then we said it cannot be always confident that a point is from the correct class because the model is constrained by the form that we give to our decision rule. So the model cannot give freely a probability for every point, but the probability is a function of W and B. So it can only adjust the probabilities of all the points as much as this expression allows for. So we'll try within the boundaries imposed by the model, the fact that we want a linear separation rule, to do the best it can to simulate the empirical class distribution. So to assign a probability 1 to the red for class 1 to the red points, and a probability 0 for class 1 to the blue points as much as possible. We've seen that this can be also cast as a minimization of our log loss, and we've seen that the log loss interpretation gives us, again, the same intuitive methods for estimating W and B. We've seen that correct classified points, we see that our loss corresponds to a sum, our objective corresponds to the minimization of a loss. The loss is computed for each point, and the loss decreases exponentially for points that are correctly classified, exponentially with the distance from the separation rule. Remember that the points which are on the separation boundary will have a score equal to 0. So Zi Si will be 0. So there are points that lie here in this plot. And those that are incorrectly classified will be penalized with a penalty that increases linearly with the distance from the plane. Imagine that I can draw my points in this way. These are the points from class 1. These are the points from class 2. This is the separation rule. If a point lies here, then this distance corresponds to a distance here in my plot. Now, the scale of the distance depends on the norm on W, but a point that is double the distance from the separation rule will be double the distance also on this loss plot. Then we have said that the model can overfit easily the training set. When the training set is easy to discriminate, it can overfit. Essentially, that's because it makes few errors, and when there are few errors, it's easy to find a solution that is very confident about the remaining points. The model does not see enough points that are in the wrong region to be able to understand that there should be points in that region as well. To reduce this impact, the impact of this phenomenon, we have introduced a regularized version of the model where we penalize solutions with large norm. Now, other questions on this part? Now, some consideration of when we use the model and how we should, if we should do something before we use the model. We have seen that Gaussian models are invariant to linear transformation, so if we use our original data set or we apply a transformation to the data set, a linear transformation that is full rank, so we don't throw away any information, the Gaussian model will still give the same solution. That's the same for PCA, so for LDA, sorry. While we've seen that for PCA, if we apply a linear transformation to our data set, that will change the relative variance of the different directions, so it will change the directions that we will select. For logistic regression, what happens? Well, as long as we don't regularize, again, the model becomes invariant to a linear transformation. If we transform the data here, if rather than using xi, we use yi equal a xi, it's sufficient that instead of having w, we put w transpose a minus 1 as new w, and then w prime transpose yi will be equal to the original. So if we have one solution for the original data, we can find a solution that has the same loss for the transformed data, which means that the two solutions are equivalent and the solution will have the minimizer of the log loss will have the same value. So we're essentially finding the same solution just represented in a new coordinate system. However, when we introduce regularization, we lose the invariance to linear transformations. Why? Because when we regularize the square norm of W, which means we regularize the sum of the square elements of W. Each of these elements is weighted in the same way and corresponds to a different component in our input space. Remember that when I write W transpose X, this is the sum of W1 X1 plus W2 X2, etc. Now, if I scale a single component of my input vector to obtain the same W, I will need to scale by to do the inverse scaling for the component of W. But if I do the inverse scaling for a single component, I'm changing the value of the regularization. Essentially, if I increase if I multiply, for example, my component, my vector x, I multiply, for example, second component by 10, that means that an equivalent solution to the one that I had with the original points will have a component in the vector w that is, to give the same solution, vector w, second component should be scaled by 1/10. But what does that mean? It means that once I regularize, this component will affect the regularization much less, which means that what happens? The model is free to give a larger value for this W to find a new solution, which will not increase a lot the regularization term. Essentially, it means that directions where the variance of the features is large will be less regularized. Essentially, the regularization will be less, will have a lower impact for directions which have a large variance, which means that the effect of regularization will depend, for the different components of my feature vectors, will depend essentially on the scale of the different components. To reduce this problem, since typically the scale doesn't, in many cases, the scale doesn't tell us anything. We have seen that in many cases the scale is just a side effect of a unit of measure that was used to compute some physical quantities that correspond to the features in our feature vectors. To reduce this effect, it may make sense when we use logistic regression with regularization to preprocess the data to reduce the differences in the ranges, in the dynamic range of the different features. Of course, which strategy we should use, typically this is decided through cross-validation. We will try different strategies that may make sense for our data set and then select through cross-validation which to use. We already have seen how to do this kind of things. One way to reduce the impact of the dynamic range, that is the impact of the scale of the different components, is to perform what is called Z normalization. So zero normalization. We center the data set and we normalize the standard deviation of each component. In this way, each component will have the same variance, which means that the effect of the regularization over the different component of vector W will be more or less the same. Another kind of normalization that I can use, which is an extension of this normalization, corresponds in making our features unit variance, but also uncorrelated. So we, rather than centering and dividing each component by its own variance, we apply a linear transformation, where the linear transformation, essentially, here there is a mistake. Here is not sigma minus 1, but it's sigma minus 1/2 A, where we transform our data so that the transformed data will have a covariance matrix. The transformed data will have a covariance matrix, sigma prime, that is the identity. So we start from our xi, which have a covariance matrix sigma I. If you apply the transformation, not I, sigma, just sigma. If you apply this transformation, then the covariance matrix for the yi's will be the identity, which means that the vector y will have its components that are uncorrelated, and the variance of each component will be 1. So it's an extension of the variance normalization. Notice that we already know how to do this, because we already know how to decorrelate the features through PCA. PCA will give us a vector of features that are decorrelated, and then once we have decorrelated the features, we just need to apply the normalization of each component on its own that will give us feature vectors that are uncorrelated and with unit variance. So with what we saw up to now, we are able to implement all these transformations already. Then another transformation that is sometimes used is the normalization of the norm of the input vectors. Again, this has the effect that input vectors will now lie around an hypersphere centered around the mean, which means that the effect of the regularization along the different components will again be sort of similar. In this case, what we do is we take a vector and we divide it by its norm, so that after the transformation, all the vectors will have unit norm. Of course, which one should we use? Should we use one to all of them, that depends on the data. So typically, it makes sense to try different combinations and then use cross-validation. We may also use PCA to reduce the dimensionality. Applying PCA, we throw away directions that are not important. That helps. Maybe we can obtain good results without having to regularize. Regularization, remember, is there to bring us solutions that are simpler. What does it mean? Simpler, that they generalize better because they risk less overfitting the training data. If my input space for logistic regression is smaller, then I may be able to obtain a good solution without the need for regularization or strong regularization. Again, is it better to regularize or to apply PCA? It depends on the data. There's no rule in general. Now, one last thing that we have not yet discussed. Up to now, we have said the decision rule for the, assuming uniform priors, uniform cost is compute the score and then compare it with 0. And this score, we have said, represents the posterior class ratio. Now, if you have followed the whole lecture on decisions, you may wonder how we have said that when we were discussing optimal decision, we said that the optimal decisions can be taken for a given application, but a given application is parameterized by a prior. So the question here is, here we don't see any prior in the decision. So how does this work with respect to what we said when we were discussing optimal decisions? What happened to the prior? Well, we said at the beginning that since the model computes class posterior probabilities, essentially it computes class posterior probabilities that implicitly embed a prior inside. The problem is we have seen that there are several priors. There is the training set empirical prior, there is the application prior, when we use a data set to compute evaluation metrics, there is the evaluation set empirical prior. So which prior is embedded in our model? We know that to have optimal decision, the prior that should be embedded there is the application prior. However, since the application prior may change and we may not even know it when we train the model, how can the model embed the application prior? It's simply not possible if we don't know the application prior in advance. So that leads to the question, which prior did we learn and what can we do with that? Well, the model is optimizing the posterior probabilities for our training set, which means that our model is actually embedding a prior that reflects the class probability, and our loss is an average, so it's the maximum likelihood for the training set data. So it's the maximum likelihood for a data set which has the sample proportions that are equal to the empirical training set prior, which means that the model will learn a model that reflects the training set empirical prior. So we can imagine that the model inside somehow embeds the empirical prior of the training set, which means that as long as the model behaves well, so as long as the model, we will see what it means in a moment. But imagine that the model worked well, we learned a good model, then the prior that we learned inside will correspond to the empirical prior of the training set. And the posteriors will therefore be optimal, will be good for applications which have the same empirical prior, the same application prior. So we need, for our posterior to be good, that the application prior is equal to the empirical prior of the training set. Let's call it like this. Now, typically we have seen that this is not the case. We may not even know what is the application prior when we train our logistic regression model. How can we deal with this? Well, we can try to recover a score that behaves sort of like a log-likelihood ratio, and then use this model in this score in the same way we discussed for generative models. We know that the score embeds the prior log odds for the empirical training set, so what we can do is build a new score that behaves like a log-likelihood ratio, that should behave like a log-likelihood ratio, by taking the score of the logistic regression. So the logistic regression score is W transpose X plus B, and now we compute a new score that is obtained by taking the logistic regression score and removing the prior log odds of the training set. So the empirical prior log odds. And then this will behave hopefully like a log-likelihood ratio, and then for an application which has a different application prior, we'll just use the application prior as threshold for our modified score. So the logistic regression, of course, if the application prior is equal to the empirical training prior, you can see from this expression that taking the original S and comparing it with 0 gives the same decision rule. So our decision rule was the correct decision rule for an application which has the same prior as the empirical training prior. However, this allows us to adapt the score to different applications with something to take into account. For generative models, we have seen that if we get a good model for the distribution of the data, then we can apply it to different applications. We don't need to retrain the model. Why? Because we see in a moment that there is no, well, once our model is correct for the feature distribution, it will naturally adapt the score to different applications. For this kind of models, that's not true anymore. What does it mean? It means that if I have a model that assumes linear separation rules, then the approach that we just said allows us to modify the model, to adapt the model to a different, let's imagine this minus, to adapt the model to different to different applications by shifting the separation rule by an amount that is what? Well, essentially, if you want the new hyperplane, if I want an hyperplane for the application pi t, it will be the original hyperplane minus the empirical prior log odds plus the log odds of the application equal to 0. This will be the equation of the decision boundaries for application pi t, which means essentially they take my original hyperplane and I shift it by this amount, which means that if the logistic regression model for the training set prior gave me this solution, modifying the model for different applications will mean that I will simply shift my hyperplane. This is similar to what we saw with the tight Gaussian model. Tight Gaussian model, we saw that changing the threshold would change just the position of the plane. I would still have solutions that are orthogonal to this plane. Now, what is the limitation of this? The limitation of this is that it may not always be good. Well, it may not always be optimal to just shift the plane for a given application. What does it mean? It means that, imagine that I have a data set that is done like this. These are the samples from class 1, and these are the samples from class 2. And let's make it a bit different. Let me draw it again. Now, imagine that we have a solution for the empirical training set prior that looks like this. And then we have an application when we want few errors from the red class. To have very few errors from the red class, I need to move my plane down. That means that I will introduce lots of errors from the blue class. If I were able to not just move the plane, but rotate it, then I can imagine that I may be able to find a solution where I still have low errors from the red class, but fewer errors from the blue one. Maybe this drawing is not the best to show, but let's draw it slightly different, like this and this. Now imagine I have a solution that looks like this. If I change just the threshold to avoid errors from the red point, I need to move my solution here, so I have errors for most of the blue points. If I'm allowed to also change the orientation of the plane, I can have very low amount of errors from the red class without having as many errors for the blue class. Now, why is this not a problem for the Gaussian, for the generative model? It is a problem for the generative model if I use the wrong model, a very wrong model for the data. So here, if I use a Gaussian model, I will have the same problem because these are not data that can be modeled by Gaussian distribution. But if I have a model that correctly models my distribution of the data, then the separation rule of the generative model will actually change shape as we change the application prior, because there will be a solution that depends on the class conditional for class 1 divided by the class conditional for class 0 equal to threshold. This is the separation boundary for our generative model. If I change the threshold, if this expression is not linear but is very complex, it will correspond to shapes that are not hyperplanes but may be complex, and the shape itself of the separation rule may change as I change the threshold t. For the logistic regression, we fix the shape of the decision rule. So we said it's linear. So that is something we can't change. And moreover, if we train the model and then try to adapt it to a different solution, the only thing that we can do is take the original trained plane and shift it, which may not be the optimal solution. I may obtain better results if I train a model directly for the given application prior. To train a model for the given application prior, I need a way to simulate the application prior so that the model tries to optimize W for a dataset that has the same empirical prior as the application prior. Now, again, as we said the other time, we don't want to change our training set, so we don't want to downsample one class so that the classes will have the same proportions as the application prior. We want to use the whole dataset, but this dataset should use to mimic a different empirical prior. How can we do this? We can do with a model that is here. No, it's before, yes, it's here. This is called prior weighted logistic regression, where essentially what we did is we split the contribution to the loss of the two classes, and then the contribution of each sample is reweighted in a way that the overall contributions of the samples of class 1 will be the same as if we had a number of samples that is proportional to pi t, while the contribution of the samples from class 0 will be the same as if we had a number of samples that was proportional to class f. So we rescale the contribution of the two classes so that the relative contribution will correspond to those of a dataset which has the same average loss for the two classes, but a proportion that is the proportion of the application data. This is similar to what we did when we wanted to compute DCF using a dataset that had a different proportion with respect to the application data. What did we did? We used a measure that keeps the average class error the same. In this case, we don't have the class error, but we have the average loss. This is the logistic loss for the logistic regression. The average loss for the two classes is assumed to be the one that I compute on my training set. And then the contribution of these two classes is weighted by a factor that is equal to the prior. Notice that if I have the prior, that is the empirical training set prior, this becomes exact, these two disappear, and this becomes exactly the average version of the log loss that we have seen yesterday. So when the application prior is the empirical prior, this model becomes the model that we have seen yesterday, the last one, the regularized logistic regression with the average expression for the loss. Of course, in this case, our score, when we train this model, our score will be a score that embeds the application prior. Again, if we want something that behaves like a log-like ratio, we need this time to remove the prior logos, but this time are the prior logos that were used for training the model. So with this model, we can control the prior we train the model for, and then we can compensate that to obtain a log-like ratio-like score. Now the question is why we should do this if we train the model directly for a given application. That's because these two processes, train with the empirical training set prior or train for a specific application, correspond to different use scenarios. If we know that we want to train our model for a specific application, and that's the only application where we will use the model, then the best thing we can do is to directly train the model for that application. But in many cases, we don't know in advance the application. If we don't know in advance the applications, we have two ways. One is we train on our training dataset, and then we compensate, as we've seen before, we train using the training set empirical prior, and then once we know the application, we will just adapt the score for the specific application. So the training is done once, then we have our model, and we will apply it in different scenarios. But we have a third option. Often I don't know the application prior T, but I can estimate a reasonable value that is close to my application prior. So I can't train directly for this application, but I may know that the application prior is very different from the training set prior, and I can get a reasonable estimate of what the value will be. In this case, it makes sense to train for a different, using a different prior for the model, so to train a regularized version of the model where I use some prior E that I estimate to be reasonably good for the application or for the range of applications that I want to use, and then I will have a model that is optimal for this prior, but if I have a similar prior, it will not be far from optimal in terms of the hyperplane that I found, and then I will just adapt the model once I know the exact, so in this case, my model will be trained with this prior E, and then I will just adapt my model once I know the actual application that I want to use it on. So I can do something that is somewhere in between. I don't know the application prior, but I can at least optimize an hyperplane for something that is probably close to the applications that I'm interested in. For example, if I know that it's reasonable that one class has much lower number of samples than the other, I may decide that I will use a prior that reflects that one class is less represented than the other, and then I will probably obtain a better result than if I trained directly with an empirical training set. Imagine that the empirical training set was balanced, so my empirical training prior is 1/2. If I use a prior that is closer to the one of my application, I will get an hyperplane that is more suited for an application where class 1 is less represented. Which means that I may use a prior weighted logistic regression model, even if I don't know the application prior, with something that estimates the application prior. But then, of course, I need, when I know the application prior, to take optimal decision for that application, which means that I will have to go through the compensation of the score that we just discussed. Now here we have some examples of some results with the same example that we have been using the rest of the course for the MNIST, and here you can see that logistic regression requires regularization. If I train a linear model in the original space, I get good results, but only if I regularize. If I don't regularize, I get much worse results. If I regularize too much, I have underfitting. And here you can see that if I apply PCA, I reduce the complexity of the model. In this case, even if I don't regularize, I get good results because the regularization is sort of done by PCA. PCA removes directions. The logistic regression model will be learned in a lower dimensional space. It will have less parameters. It will have less opportunity to overfit. In this case, regularization becomes less relevant. And we can see that we obtain better results than what we had with the tied model. Questions up to here? Okay, then we will go quickly through this, but because I want to finish also another part, but we can then extend our model. We have seen the logistic regression for binary. We can now extend the model to multiclass. Now we assume we have k classes labeled 1 to k, so numbers. Again, we need to provide an expression for the class posterior probability for each of the classes. And in this case, again, we take inspiration. We're not deriving it from. We're just taking inspiration from the generative model. As we did for logistic regression, we took inspirations to see what can be a reasonable expression for the class posterior probability. We derived it assuming that there was a linear separation rule, and that was inspired by the tied model. Let's go back to the Gaussian model and see how it works for a tied Gaussian model for a multiclass problem. For a multiclass problem, we can show that the Gaussian model gives us class posterior probabilities that are a linear function of our x plus a bias plus a constant that depends on x but does not depend on the class. So what do we have here? We have a vector w that depends on the tied Gaussian model parameters, a vector b that depends on the tied Gaussian model parameters, and a function k that does not depend on the parameters or the class. And this vector w depends on the class. So each class, if I take my tied Gaussian model and I rewrite its expression, will lead me to an expression of this kind. Wj is essentially proportional to minus 1/2 sigma minus 1 mu j, and bj, or plus, without the minus 1/2. And bj should be something like that, plus some other constant that we don't care, again. You can write this explicitly starting from the log likelihood and see what do you get as a result. This is exactly the kind of expression you will get with w depending on the sigma, the share sigma, and the mean of the class. Again, this is an affine function it's a linear function in w. It's an affine function, at least this part is an affine function, plus something that is not affine in x, but does not depend on the class. Since it does not depend on the class, it means that the class posterior probability is proportional to the exponential of this. So it's exponential of k of x times this. But this k of x does not depend on the class, so it's the same expression for all classes. So for class Cj, I will have exponential of the constant, exponential wj transpose x plus bj. Now, I should compute the exponential of kx, but I don't want to do it. To avoid doing it, we remember that we have a closed set classification problem. So the sum of all the class posterior probabilities should be 1, which means that if I rewrite the expression for all the classes, this should be 1. I take this outside, and I get this expression. The proportionality factor between the class posterior and this term has this form, which means that now I put this in place of this exponential of k of x, the class posterior probability for class k is exponential of w transpose k, wk transpose x plus bk divided the sum of the exponential of the wj transpose x plus bj terms of all the classes. Essentially, you can imagine that, remember that for the binary we had a score for the point that was looking like this. Here you can imagine that to each class, if I have a vector xi and I have k classes, to a vector xi I will associate a score vector this time, where the first component is the score for the first class, then the second component is the score for the second class, up to the score for the kth class. So each sample will have actually k scores, 1 per class. And then these scores are related to the class posterior probability through a function that is called softmax. So for each class, I will compute a score, and then the class posterior probability will be what? I will take for class J the score of that class, take its exponential, and then everything will be divided by the same quantity computed for all the classes. So I take these scores, I exponentiate them, then I sum them, and then I divide each of them by their sum. This gives me the class posterior probability. Notice that this is more or less what you were doing when you were computing class posterior probabilities from class conditional likelihoods. These indeed are terms that are proportional to the class conditional likelihood times the prior, so to the joint probability. When you were doing the class posterior in the laboratory for the Gaussian models, you were doing exactly this. For each point, you were computing a class joint probability, then you were taking exponential of that, summing the values, and then dividing each term by the sum. We were doing it with the log sum x function, this process. This is exactly the same. We have a model where these are proportional to the class and label joint probability. The class posterior probability is obtained by taking the exponential of these terms and dividing it by the sum of those exponentials. This specific function is also called softmax, which is a bad name because it should actually be called arg softmax, because it does not do the equivalent of a max. It does not select one of these terms as value, but essentially will give a value that is close to 1 for the highest of these values, but in any case, that's how it's called. It has the property that if we have one score that is much larger than the others, then the class posterior for that, corresponding to that, will be close to 1. So essentially, it's a function where if I have a score that is large for one class, it will correspond to a class posterior for that class that is close to 1. While when all the scores are similar, the class posterior will be close to 1 over the number of classes. If I have a class whose score is lower than the others, or any other, then the class posterior for that class will be close to 0. So we now have a model for the class posterior probability of class K. Again, this was inspired by the logistic regression, by the tight Gaussian model, but we now forget about the tight Gaussian model. We assume that this is the expression that describes our class posteriors, and the model parameters are the model the parameters that describe the linear combination of the features for each class. So for each class, we have a vector that describes a linear combination of features plus a bias. These are the models of the parameter. Then we will give a geometrical interpretation to this as well. This is therefore the expression of the class posterior probability, and the model parameters are the different W's. As we said with the binary model, once we know W and the matrix W, so all the vectors W and all the biases, that allows us to compute the class posterior probability of all the classes. So we have a distribution where our class can be 1 out of k, and we are able to compute the class probability for all the classes. Which means that essentially this class Ci, the class posterior, the random variable Ci given Xi is distributed as a categorical random variable whose parameters are what? The parameters of the categorical random variable are exactly the probabilities of each class. But the probabilities of each class are exactly the softmax element. So if I have feature vector Xi, you will have an associated vector Yi that contains the terms exponential of W transpose 1 Xi plus B1 up to exponential W transpose K Xi plus Bk, each of these divided by the sum of the exponential. So the result of the softmax function applied to the scores computed for that sample. Here I is the sample and k refers to the component of this vector. And these are the parameters of our categorical distribution. Then we can compute our parameters as to maximize the log likelihood. The idea is the same as for the binary case. When we derived the log likelihood expression, we didn't do any assumption on the form and on the distribution of the class labels until we actually replaced it with a Bernoulli. So up to that point, the derivations are the same. We can optimize our model by optimizing the likelihood of the class labels given the feature vectors. So again, the maximum likelihood becomes a maximization of the likelihood of the class posterior probability of the logarithm of the class posterior probabilities given the feature vectors. Now, the difference between this and the binary is that now here we should use the proper model for the class posterior. In the binary, this was a Bernoulli, so we use the Bernoulli density to represent this. Here we have a categorical. A categorical, remember that we can express a categorical distribution in a way that when I introduced it at the beginning of the course, I said it may look strange to use this representation, but it will make sense later. We already saw when it made sense with the multinomial model. Here, we will use it again. If we have a categorical random variable, we have that the probability that the class is Ci will be equal to yi Ci, so the component Ci of the vector of probabilities. We can represent this probability using a 1 out of k encoding of the label. So rather the label Ci will be encoded with a vector that will have what? All elements zeros except a single component 1 in the position Ci. So this is the Ci's position. Well, Ci is plus 1 because we count from 0, but let's say we have 0th, 1st, etc. position. In index Ci, we will have a single 1. Then if we have a single 1, we can represent the probability that the categorical random variable is equal to Ci as the sum over all classes of the Zi vector that is associated to the class Ci times the vector, sorry, this is the log probability, the Zi vector times the log probability of the corresponding class. Again, this is the log probability of the class being Ci. This vector will be all 0 except the component that corresponds to the 1, the component that corresponds to the 1 will have the small k equal to ci. So the only element in this sum that will remain is logarithm of y ci, which is exactly the logarithm of the class posterior probability. 1 out of k encoding of the distribution. So this is just a compact way to express the categorical random variable log probability using a label representation where each label is represented by a vector which has all elements 0 except a single element 1 in the position corresponding to the class. Now that we have this expression, remember these yik, we already know them. They are given by the model. We know the expression for the yik. This is yik. We replace these expressions in our log likelihood. Our log likelihood becomes a sum of the samples of this second box, is the log probability of ci given ci equal to small ci given xi equal to small, this big ci and this small ci. So the probability that the class label is the one that I actually observed given the feature vector. And then I have a sum over all samples. Now the thing that I need to do is replace this yik with the model, with the expression given by the model for the class posterior probability, and I get exactly the expression that I want to optimize. I want to optimize this expression, which is a function of the model parameters w and the bias b. Now, this is a maximum likely solution, and we will not develop it because developing it will not give us any particular interesting insight. Just this is the function that we want to optimize. These are functions where w and b are unknown, but those are the ones that we want to optimize for. So those are the variables we are looking for. And everything else is known because the xi's are the samples, and these are the class labels encoded as vectors. Now, as for the binary problem, we can show that this expression corresponds to a cross entropy, so the negative of the log probability corresponds to a cross entropy between the observed and predicted label distributions as for the binary case. So we have that the yk gives us the probability of class being k according to the recognizer, just being k, while zik is the probability that the class is equal to k according to somebody who knows the actual label of the class. This will be 1 only for the correct class of the sample. So again, maximizing the log likelihood corresponds to minimizing, we have a minus here, the cross entropy, which means that we can estimate the model in the same way, in a way that tries to match the probabilities as computed by the recognizer to those that somebody would give when he knows the correct label. If I know that the correct label for my sample is 0, no, sorry, it's 2, then I will say the probability that the class is 0 is 0, the probability the class is 1 is 0, and the probability the class is 2 is 1. This is exactly the values of the vector zik. Zik will have 0, 0, and 1 as values. While yik have the same probabilities as computed by our model. So our model is trying to match its own predictions to the empirical correct predictions for the training set samples. Now, you may wonder, well, let's see first this. Then, as for the binary, we can represent the cross entropy as a loss computed over the samples. In this case, we will not see the details because casting it as a loss, which is called softmax loss, does not show us something that is particularly interesting because looking at this expression doesn't tell us much more than just looking at this expression. So in this case, we know that it can be expressed as a loss as well, but we don't have much to gain by doing that So we'll just skip that. The thing that we want to know is how is this related to the binary model. First of all, there is already a discrepancy. In the binary model, we had one vector W and one bias. If we apply this multi-class model to a binary task, we have class 1 and class 2. But now we have two vectors W's and two biases. So it's not the same model as the binary model if you apply it to a binary problem. How is it related to the model that we saw before? Well, it turns out that if we have a K class problem and we parameterize with a set of K vectors W and K biases, we are over-parameterizing the model. What does it mean? It means that we can always obtain an equivalent model by setting one of all the W's equal to zeros and one bias equal to 0 as well. That is, we are representing the model with a number of parameters that is more than we actually need. To give an example, imagine you want to represent a linear function. These are the parameters that you can use to represent a linear function, but you can over A and B are the parameters. You can over parameterize your linear function by specifying two values A and C that both multiplies a linear term. These are an over parameterization of the function. We have given a value of A and C that are optimal. We can find an infinite number of values A and C that are also optimal by simply playing on the values of the two parameters. This is called over-parameterization. We use a number of parameters that is larger than the minimum number of parameters that we need to obtain the same expressivity. So to obtain a model that can give us the same, that has the same representation power. Here, using both A and C does not give us anything more than using just a single parameter A. It turns out that this is over-parameterized, but in a multi-class task, we don't really have a reason to choose a single class as the one that should have a W and B that is fixed. For the binary, we can show that if we take a multi-class solution and we compute these two terms, and we call this W and this B, this will correspond to the solution of a binary problem. A non-regular, if we are considering a non-regularized model for the moment. So actually, the two models are related in the sense that the multi-class is a over-parameterized version of the model, and for the binary problem, it's also over-parameterized, but if we compensate for the over-parameterization, we obtain the same solution as for the binary problem. So the two are solving the similar task. Then, as for the binary, the model can overfit. So it may be worth to add a regularization term that will penalize solutions that are too complex. Complex in the sense that will make our model too confident. Or, if, as we will see later, may also represent, now it doesn't make sense, but may also represent more complex separation surfaces. For the moment, it doesn't make sense because everything we saw is linear, but with what we will see next, it will make sense why also, well, with some of the things we will see, it may make sense why having a low norm of W corresponds to smoother, to simpler separation rules. For the linear model, let's just say that it's simpler because it leads to less confident solution. It avoids overconfident solutions. A possible regularization is to add a regularization when I penalize the norm of each vector W. And then I sum the regularization terms applied to each of these vectors, which is the same as penalizing the norm of the matrix W, which would correspond to the same thing. And again, if we need, we can use a prior weighted version of the model where we replace the averaging of the cross entropy with an average that is weighted by the prior of the application that we want to simulate. So similar to the binary. Now, why is it in the why this model is still in the slides? Well, no, it's not because. Yeah. How is this model related to the logistic regression? Which kind of solution it gives for classification? Well, it's considered a linear classification model. Well, first of all, we have seen that there is a linear relationship between the class posterior and log posterior probabilities and the values x that are relevant for the classification. So if we ignore the constant part that does not depend on the class, the rest of the expression for the class posterior is linear, affine in x. This is the part that controls our classification rule. The score j, for example, x, is an affine function of x. We can show that for how the model is defined, we have that classification boundaries, so the points at which we change our classification rule are as well linear functions that correspond to pairwise difference of the vectors w's that make up the classes. We are not going to prove this, but these separation rules depend on the vectors w's of the classes that they separate. So decision boundaries are the boundaries at which I change my prediction. So, for example, in this region, imagine the cost of errors is the same. In this region, the class posterior probability is highest for class red. Then, if I move here, the class that has highest posterior probability becomes class green. Then, if I move here, this region is where class blue has the highest posterior probability. The boundaries where I change the class that has highest posterior probabilities are piecewise linear functions, as in the tied Gaussian model. But of course, these do not depend on the distribution, are not estimated from a model of the distribution of the features, but are estimated to optimize the separation boundaries between the classes. So for this, in this sense, this model is still giving us linear classification boundaries in the sense that they are piecewise linear, and the boundaries where I change point sample are linear. When I change the class, the predicted label are linear. Now we can see this applied to the MNIST model, and we can see that again, if we don't regularize, we don't reduce with PCA, regularizing is important. In this case, reducing with PCA makes us lose information, so PCA is not effective in this case as a way to regularize, so the best thing here is to use the original data with some regularization, and we can see that this model, despite being linear, does much better than our tight Gaussian, which is also the same kind of separation rules. Why is that? Because here we have a data set where the input features are images that contain black and white pixels. Black and white pixels, we have said, are not well modeled by a Gaussian density. If you look at the marginal for one picture, we will see that most of the picture, okay, not exactly black or white because we have levels of gray, but we will have that a single pixel from class 0 will be a pixel that has some samples where the pixel is white and some samples where the pixel is black. If we plot a histogram, we may have an histogram like this. If it's a pixel that is always white, then we will have something like this. If it's a pixel that is always black in all the images, we will have something like this. If it's a pixel that sometimes is black, sometimes is white, we'll have histograms that look like this. In any case, these are not well modeled by a Gaussian. Here a Gaussian would do like this, and here a Gaussian would do like this. So our Gaussian model is able to get, in any case, something out of that. Why? Because these parts are not that badly modeled as they may seem, but a model that does not rely on the distribution but optimizes directly the separation rule here has probably more power to find a good separation rule without caring on how the pixels are distributed among the different classes. Of course, this requires that I have more data to get a robust estimate of the class posterior probabilities. So if I had a good model for the feature for the pixel distribution, I would probably obtain good results with fewer data, but here, unfortunately, I have lots of data compared to the number of samples. Adding some regularization, I can obtain results that are better than a generative model that does not really model well the feature distribution. Okay, questions up to here? Okay, then we see this last part. The last part addresses the problem where we have seen that logistic regression does better than the tide model. However, we already know that the MVG model was much better than the tide one. So we saw that using MVG, we obtained much better than the tide and also much better than the logistic regression. Why? Because we had a model that was not that accurate for the feature, but was accurate enough and was more powerful because it was able to account for variations in our dataset that cannot be captured by simply linear relationship. What does it mean? It means that the Gaussian model can give us quadratic separation rules, and these quadratic separation rules, in this case, adapt better to separating the samples of the different MNIST classes. Here, the model does not require assumptions on the feature distribution, but in any case, it can't do better than having linear separation boundaries. So it can't have, if I need nonlinear separation boundaries, imagine a data set where we have two classes organized in this way. Even if I don't know the distribution of the data, I can try as much as I want. If I try to separate these classes with a linear plane, I will never do good. Here, even a Gaussian model that is multivariate, that is not very accurate because it will estimate two Gaussians like this, which means it will put strong emphasis, a strong amount of probability in regions where the samples are absent from both classes. In any case, we still do a better work because it will estimate separation boundaries that look like this, and therefore, even if it's not a very accurate model for my data, it will still accurate enough that it's able to capture the part of the distribution that is relevant for the classification. It's able to find this kind of separation rule. A logistic regression model, linear logistic regression model, here will never be able to do this thing. It cannot, simply can't. However I put my separation, I will have lots of errors from at least one class. Question is, how can we then find a way to get the same benefit of more powerful separation rules with the benefits of a discriminative model that does not require us to have a good model of the feature distribution? The answer is yes. However, it will lead to models that become more complex and, as such, will tend to overfit even more. How can we do that? Well, let's start again from the way, and let's do it for binary just only. We start from how we derived the logistic regression model. For the logistic regression model, we assume linear separation rules of this kind. We said this is the model assumption, but nothing forces us to choose a linear expression here. For example, we know that if we have a Gaussian model, a generic Gaussian model, separation rules have a quadratic form. So the idea here is, since we know that we can have quadratic separation rule, why don't we assume quadratic separation rules instead of linear? Remember that the model, the logistic regression model, we assumed the form of this expression, which leads to the separation rule. We can, but nobody told us that this should be linear. That's what we decided to have. Here we can choose to use any function of our input and some parameters. Let's call the parameters p. So why not a quadratic function? We know that a quadratic function is good for the MVG, so why we can't use a similar separation rule for the logistic regression? Well, we can. We just assume that this is the separation rule, and then what changes? Well, with respect to what we did, nothing changes. We could go back, take the set of slides we did when we derived everything about the logistic regression, replace every time we had W transpose X plus B, replace it with X transpose AX plus B transpose X plus C. That is, this was the score for the linear logistic regression. Now we assume that the score is this new function, and then nothing would change. We would have a model where this is the score. The class posterior probability for class 1 would be the sigmoid of the score. Then our log likelihood would be what? Sum over samples of Ci logarithm of sigmoid of the score for sample Xi plus 1 minus Ci logarithm of 1 minus the sigmoid of the sample for Xi. Before Si was linear, now it has this expression, but nothing has changed except that when we try to optimize the model, we'll now optimize it with respect to A, B, and C. So we will write our optimizer so that when it computes S, given the model parameters, it will use this expression to compute S as a function of the model parameters. This will give us a quadratic separation rule that maximizes the likelihood of our training data. And then, of course, we use that function to compute class posterior probabilities, or if you prefer, our decision rule becomes this. Or if you want a log likelihood ratio, I'm writing this quickly because it's exactly the same things that we wrote for the linear model, just hiding the model inside S. Everything we did could have been written in this way, just saying at the end S is equal to this expression. Now everything is the same, but with S being the quadratic expression. Now this is interesting because it gives us a way to solve the problem that then can be generalized because we can make this function S arbitrarily complex. We'll say a couple of words. Another way in which we can obtain the same result, which is, well, gives us another intuition how we can achieve nonlinear classification, and that we will introduce because we will use next week, is to observe that we can also obtain, this is another way to obtain the same solution. If we analyze this expression, we can also observe that it's a quadratic expression in X, but if we look at it as a function of parameters A and B, it's actually linear in A and B. What does it mean? A function is linear if this is true. Now imagine that I have S of X of A plus B here, etc. This is equal to the sum of the scores. So in terms of the model parameters A, this is a linear function. We can actually express this linear function in this way. Here I have X transpose AX, which corresponds to the trace of X transpose AX interpreted as a 1 times 1 matrix. Trace is circular, I can bring this X on the other side. And then I use the fact that trace of AB can be expressed as the scalar product between matrices A times B. What is the scalar product between two matrices? It's the sum over all the elements of Ij, Bij. It's the same as the scalar product of vectors, but this time extended to all the elements of the matrix. I take my two matrices, I do element-wise multiplication of the corresponding terms, and then I sum all the n times n results. And if you want, it can be expressed in a vector form by writing the dot product in this way. What is vec of matrix A? Well, imagine you have matrix A that consists of columns. Vec is the operation that takes these columns and stacks them. So we can also write it as a vector product if we take the matrix A and we stack its columns. And we do the same for the other matrix. Here in our case, matrix B is X transpose. Which means that if we now define phi of X as this vector and W as this vector, what do we obtain? We obtain that the score can be written with this expression, which is, once more, a linear model, but a linear model for the features phi of X. So if I take my X and then X vector, and then I compute phi of X that contains all these terms, and I use a vector representation of the parameters W, I can express my score as a linear function of this phi of X plus a bias. Which means that this corresponds to a linear logistic regression model trained over the vectors phi of X. That is, I can imagine that this corresponds to the what? Start with my data set, first perform a transformation of my data, that is, transformation to this linear function phi, and then I will have my vectors phi of x1, phi of x2, etc. And then using this new data set of the vectors phi, I will train a linear logistic regression model. So I will train a linear model over a set of transformed features. This will correspond to what? To a linear classifier for the vectors phi. When I need to test a sample, t, I will do what? I will compute its transformed version phi of t, and then I will compute its score using the transformed vector. So everything looks like a linear logistic regression model for the transformed features v, phi of x. But this model, this is also called, phi of x is also called expanded feature space, because it's a feature space that typically is of a much larger dimension than the original feature space. For example, here if we have r to the power d as x, phi of x will be in r to the power d times d plus d more. A linear model in phi of x is the model that I will use, but this linear model actually corresponds to a quadratic separation rule in the original feature space. So we obtain that, for example, to learn a quadratic separation rule, we can perform a nonlinear expansion of our vectors, learn a linear separation rule in the expanded feature space. This linear separation rule in the expanded feature space will correspond to a nonlinear separation rule in the original feature space. All that we need to do is to compute the feature expansion. Problem is that this approach leads to computational issues very quickly because, for example, here we have seen that we can obtain quadratic separation rule using this expansion, but the size of this is d times d. If we want a separation rule that is a polynomial of degree 3 form, so the separation rule should be the solution of a degree 3 polynomial equation, then this becomes d to the power 3. If I want 4 degree separation rule, it becomes d to the power 4. This is the original feature space. So if I want a degree d for a polynomial separation surface of degree d, small d, then I will have this complexity in the expansion. So computing the expansions can become fairly expensive. Notice that even using this approach would lead to a growth. In this case, the growth would be in the size of the parameter vectors A as well, because the parameters vectors are the same in the two approaches. Here I do train a linear model in expanded feature space, but the parameters are the same. Here they are represented as a vector, here they are not, but the number of parameters is exactly the same. And I can go from one to the other. So this approach is typically not directly usable. We can still use it for quadratic methods. Here you can see that we have a logistic regression with quadratic separation boundaries. This is the multi-class version of that, but we didn't change much. We can train a quadratic logistic regression by doing quadratic feature expansion and then training a linear multi-class logistic regression model in the expanded features. This will give us separation rules that are pairwise quadratic. And we can see that this leads to much better results than the Gaussian model. But we can see that the regularization becomes probably even more important than before. Consider that here I'm using PCA. Why am I using PCA? Because the original space was 760. The expanded feature would be the square of this. While using PCA, here it's not done to avoid overfitting, it's done to reduce the computational complexity of the model. The model with PCA still has an input feature that are the expanded features that are 2,500 dimensional. So they are already 3 times larger than the original features for the linear model. And you can see that in this case, regularization is important because PCA is simplifying this transformation, but then I still have a large input space for the logistic regression model. Why is it large? Because it corresponds to quadratic separation rules. Quadratic separation rules are more complex than linear. So I have much larger amount of parameters. I have many more ways I can put a quadratic separation rule than I can with put a linear one. They are more powerful, so they are also more prone to overfitting. In this case, even if my original input space is very small, since the expanded feature is large, I need to add regularization to avoid overfitting. But if I do that, I can obtain results that are less than half the error rate that I got with the Gaussian model. I don't rely on an assumption on the feature distribution that for the Gaussian model was fairly inaccurate. So I gain from both the best of both models. Now, and then here is where we close this lecture. We'll see next week with the computer science guys, so should be all those who are here, how to perform these feature expansions in a way that avoids the feature, that follows the same framework, but we will not explicitly compute the expansion. So we will do exactly this process, but we will do it in an implicit way that will allow us to avoid the exponential, the computational cost due to the increase of the input feature space. And we will see how to do it with a model that is called super vector machine. On the other hand, the other approach that we said at the beginning, use a generic function that is parametric here, would lead to another model that is a neural network where essentially we would put here a parametric function that is sufficiently complex that would give us the score for our logistic regression model, and then use the logistic regression model to actually compute the optimize the parameters so that the model optimizes the probability of the training set class labels, but with respect to a function that is complex enough that it can give complex enough. In the case of neural network, I can make it complex enough so that the separation rules become arbitrarily complex, smooth but complex separation rules. Of course, this means that the more complex the separation rule I can allow my model to have, the more data I will need to avoid getting wrong results due to overfitting. So neural networks allows me to make this function more complex. The problem is I need, in this case, to have even more data than what I need for simple rules to avoid that this model actually learns something that is not useful for unseen data. Okay, questions? Okay, so that's all for today.